recording.
So, okay, let's start the two last talk of today's session. So we have a great pleasure to have with us Professor Roberto Triggiani. So thank you very much for accepting the invitation. And Roberto Triggiani is a professor, a distinguished professor at the University of Memphis. He's a specialist on control theory of partial differential equations. Uh, he has plenty of academic merit and award, several published books, and a big amount of research papers. So we are very honored to hear you. So today he will talk about uniform stabilization in Besov spaces with arbitrary decay rate of the magnetodynamic system by finite-dimensional interior localized static feedback controls. So thank you very much, and you can.
Yeah, thank you very much, Anna. Thank you, the organizer. Sorry for the long title, which may create some problems. So let me attempt to analyze the title. So first of all, there's going to be a stabilization in the uniform topology of a certain underlying space, which will be a Q-based or a Besov space. And I will talk about this Besov space later on. The procedure provides an arbitrary fast decay rate, and the dynamic is the MHD equation, Magnetohydrodynamic equation system. By means of what? By means of controllers which are in feedback form, so closed loop, not open loop, the same way the thermostat works. They are static rather than dynamic, which means there's no dynamic equation in the loop. And interior localized means that the support of these controllers is arbitrarily small in the interior. And very important in the whole issue here is that they are finite dimensional. In fact, will be minimal dimension. Okay, so this is a continuation of work of the last few years, along with some other work with Irena Arshevska and our first PhD students, Budika, here in Memphis, about the uniform stabilization of parabolic fluids. And the emphasis is to find explicitly constructed controllers which are localized, so the support is arbitrarily small, static rather than dynamic in the interior or on the boundary, depends on the situation, which I will describe in a second. And most important, or equally important, they are finite dimensional, in fact, minimal dimension. So I mentioned here a few papers in, in this line of research. And let me start with the Navier-Stokes dimension 2 and 3 in LQ or Sobolev or Besov, initially with interior localized in this paper here. Now, why Besov? The reason of Besov is in the second paper. One is to mention that the stabilization of the Navier-Stokes equation was initiated by Andrei Fursikov in the early 2000. His work generated interest in the area, in Europe and also here in US, but the feedback was not a closed loop or stabilization open loop, and the feedback was not even thought to be finite dimensional, let alone explicit. Okay. However, that work generated interest in the problem. So after many years, there was still an open problem in dimension d equal 3 about the stabilization of the Navier-Stokes equation. And it was resolved in this paper, the Archive Rational Mechanics and Analysis, where the presence of the use of the Besov space, which is the first time was using this problem, is essential for dimension d equal 3. I will be more specific later on, but right now I want just to say what is the magic of Besov space. So you need the Besov spaces with a very tight index, which I will mention later, which satisfy two competing characteristics. On the one hand, has to be sufficiently low topology in order not to recognize compatibility condition. At the same time, has to be the topology is to be sufficiently high for dimension d equal 3 in order to analyze the nonlinear well-posedness and stability question. So whoever wants an interest about this problem, I do have the transparency of a talk I gave in Berkeley in 2001, and I can send, if somebody asks me, send me an email, I can send my 60 minutes talk on this. After doing the Navier-Stokes, you just move on and you do the Boussinesq system, which coupled the Navier-Stokes with the thermal equation. And again, initially we do the Besov. So the Besov is at the interior is not essential, but is a teaching ground. It is a testing ground for the techniques and for in order to do eventually the boundary based. So for the Boussinesq, initially we did again the interior in the Besov, but then later on we did in this paper we did the localized, we did the boundary, but boundary only for the thermal. And next time, the next thing we want to do the boundary for the fluid. And the controllers are supported in an arbitrary small portion either of the boundary or of the interior. And in all these things, the tremendous importance is played by the maximum regularity of the abstract equation, as I will mention later. So we start with the domain D in connected dimension 2 or 3 physical. Omega is a small arbitrary small open subset in the interior. M the characteristic function, D is the velocity field, pi is the pressure, scalar pressure, D the magnetic field, and this F and G are the perturbed exterior forces. So the equation, the MHD equation in question is given here. So we have a y, the Navier-Stokes with the pressure. This is the nonlinearity of the Navier-Stokes, coupled with the magnetic field, the B here. And on the other hand, the B equation is coupled, everything's nonlinear here, is coupled with the y, with this term. And the right-hand side produces or shows the control U and V on the two equations with support on an arbitrary small little omega because of the characteristic function. And then there are divergence free on both, okay, on both unknowns and then the boundary condition. So the usually I wrote this minus Laplace, usually is written curl B, but there is divergence B equals 0, so this becomes minus Laplace. Okay, so what is the wait a second here. What is the general, part of my screen is not visible, at least to me. But what is the general strategy? The general strategy is well known since the parabolic of many years ago. So you want to identify the implementation of the strategy is maybe, in fact, it is very complicated technically and also conceptually. You want to identify the linearized problem in an abstract form. Once you do so, for the problem to make sense, you want to assume that the linearized problem, because of the various quantity sigma sub f, sigma sub m, etc., be unstable in a sense that will be made more precise later. In particular, this means that there is an unstable stationary solution. And then you work with this unstable stationary solution. There may be many, but you pick up one. And then you concentrate initially on the linearized system. And here you apply a strategy that was introduced for parabolic, for abstract parabolic in my PhD thesis in 73 at the University of Minnesota, which I will review. And at the very time t equals 0, at the outset, there is a difficulty, which I will mention as we go along. And what you want to do, for the linearized system, you want to construct the closed loop. You want to show that the closed loop is well posed in the sense of the linear semigroup. Moreover, it's uniformly stable in the desired functional setting by constructing appropriate finite-dimensional interior localized static feedback controllers. So, and once you take care of the linearized problem, you move to the nonlinear problem, and you apply the same feedback mechanism, which with this property that we desire, which work for the linearized, and hope they're going to work also for the nonlinear in the local sense. And so you wanted by using the same feedback mechanism, everything is constructed here in finite dimensional, so that the resulting closed loop nonlinear problem is locally well posed in the nonlinear semigroup sense in LQ or this Besov space. And moreover, here's the final thing, is uniformly stable in the neighborhood, in the vicinity of the unstable stationary solution. Okay. What are there are some number of technical problems that arise, and I single out only two, one for the linear and one for the nonlinear. For the linear analysis is that this procedure that I was mentioning, which is based on the decomposition of the space, taking into account the parabolicity of the dynamics, you end up immediately with the desire to stabilize the unstable finite dimensional, not only stabilize, but you want to stabilize it with an arbitrary large decay rate. That's very important. In order to do that, you need, you go back to this control theory of the 70, and you need a Kalman algebraic rank condition for this PDE problem. But the issue is not a matrix theory. It took some time, at least to me, to discover that this verification of the Kalman algebraic rank condition for the finite dimensional unstable is related to a unique continuation property of the corresponding static eigenvalue problem, subject, however, to an overdetermined condition in the interior. I will mention this. And the solution of this problem is in this paper, this recent paper, and is based critically, is very technical, is based critically on Kalman type inequalities, which originally I was doing for the Navier-Stokes. And I will mention a little bit when we get to the appropriate time. And I wrote a paper of 90 pages or so on this fluid dynamics in Prague, which is entitled Unique Continuation Property of Static Overdetermined Eigenproblems is ignition key for uniform stabilization of dynamic fluid by feedback controller, okay? And here I do the heat equation, the Navier-Stokes, the Boussinesq, et cetera. Once you do this for the linear analysis, you move to the nonlinear analysis. And here, you want to show well-posedness, a uniform stabilization locally. And one thing that comes in the context of this LQ of Besov space is that you want to show that the linear operator, feedback operator that does the job for the nonlinear, which has been constructed for the linear or for the linearized, has the following property: not only generate a strongly continuous analytic semigroup in the LQ, so sigma is a solenoidal component, but moreover, or perhaps in Besov, but moreover, it has the property of maximal LP regularity and up to T equal infinity because it's uniformly stable. Now, the difference between Hilbert and Banach has been known for a number of years. In Hilbert space, there's a result of my countryman, De Simone 65, in Italian, which I read, by the way, many years ago, which shows that the generation of analytic semigroup is equivalent to maximal regularity. But this is not true in the Banach setting. Maximal regularity implied, but is not implied. And by the way, at the abstract level, there are still open problems here. Let me start with the initial point of the analysis. The initial point of the analysis is to look at the stationary problem, which is given here. The quantity depends only on x. The derivative with respect to time has been eliminated. Sub B means equilibrium. And there is this result, which you see is 2020, is very new for the MHD equation, which says that if you start with the f and g, the forcing term on the right-hand side of the regularity LQ, then you gain two derivatives for the equilibrium solution of the y, two for the equilibrium solution of the magnetic field, and one for the pressure. And there is a solution, and the solution, like in the case of the Navier-Stokes, is not necessarily unique. And then you pick up one and you work with that. Okay. A first step of the procedure, since you want to study eventually for the nonlinear problem, you want an analysis in the neighborhood of the equilibrium solution, which has been produced by this theorem just mentioned. Then you just make a translation. You translate the state, the fluid, the magnetic field, and the pressure by the equilibrium solution, and then you rewrite the equation. The new equation has the advantage that the function f and g disappear, they are cancelled off. But the price that you pay is that, like in the Navier-Stokes, of course, is that you get additional terms. Here, the Navier-Stokes is perturbed by the Eocene perturbation, which is a first-order operator with respect to z, Y sub B and B sub B are, or curly B sub B are known, are obtained from the equilibrium solution with which we work. And so you get additional term, make the equation more complicated in response to the fact that the function f of g have been eliminated. Then you look at the translated, so this is a translation for the nonlinear. Then the nonlinearity is here, the nonlinearity is here. You eliminate the nonlinear term, and then you look at the translation of the linearized, and you call it this W for the fluid, and curly W for the magnetic field. And MU and MV are the control localized in this little omega in the interior. Then, so there's no point to put all this operator, there are plenty, but just to give you an idea, so L plus YE means simply plus is here, is the Oseen perturbation first order. This is for the fluid. This is the Oseen perturbation with a plus for the magnetic field, and this is with a minus and minus respectively. So you write everything in terms of the equation, and you rewrite, then what do? You want to eliminate the pressure, which is here. And you do the usual Helmholtz projection. So, but we are not in Hilbert space, so we are in the Q. And so given omega, you want, you seek the Helmholtz for the decomposition of the space in a direct sum of the solenoidal vector space LQ sigma and the gradient field. And the operation, the projection is the projection, Helmholtz projection. So anything here is the gradient of something sufficiently smooth. So when you project, the pressure disappears, and so you work on LQ, so like in the Navier-Stokes. Okay, so the thing to say is that this LQ sigma is an element in LQ, is divergent free in a sense of distribution, and it's very important that the vector here is tangential to it's a part is intrinsic this description of the space. The G is tangential to the boundary. Okay. Now there is an issue that you need some assumption on the bounded domain, and there are some counterexample where this doesn't true for PQ different from 0, but I will not insist into that. Okay. So you eliminate you apply the Helmholtz projection to both equations. And there are a bunch of operators, which I will just, I will not go through them for sure, but this is just the Stokes operator for the fluid. This is a Stokes operator for the magnetic field. So it's the Laplacian acted upon by the projection, Helmholtz projection. And then there is the perturbation first order for the fluid and for the, these are all first order perturbation and for the magnetic field. Okay. Then you rewrite the nonlinear translated in terms of this after eliminating the pressure as a diagonal driving operator and the perturbation, which is a first order. And then, of course, this is the nonlinearity in both variable, the fluid and the magnetic field. And then this still the controls, which have not been touched yet. And then, so taking the divergent field, you write this as an abstract equation. So the operations become operator. And so these are the operators, which are the Stokes operator for both of them. And this is the first order perturbation, and this is nonlinearity. Okay, now you concentrate on the nonlinear problem. And so with the initial condition. And what you want to do here, first of all, you look at you recall the standard well-known property about the Stokes operator, which of course in LQ generates an analytic semigroup, is uniformly stable. But then when you perturb with the first order perturbation, you retain analyticity, but you lose, of course, decay. And you do the same thing with the magnetic operator. And therefore, when you put the dominant operator for the coupled system, which is given by the two Stokes operator, this again is generate analytic semigroup on the LQ, and it is analytic, of course. Okay. Then, however, you perturb with the first order perturbation, and you preserve analyticity, but you lose, of course, stability. And here now we can finally talk about the stability problem. So you have the linearized feedback, the linearized problem, which is a generator analytic semigroup, so the compact resolvent, and therefore the spectrum is in the classical triangular sector. So you call lambda 1, lambda n, you make the assumption for the problem to be significant, depending on the quantity in the equation, that the problem is unstable. Unstable means that the linearized has a number of eigenvalues on the right-hand side, here L1, Ln. And then you order according to the decreasing real part. And then you apply, then you apply the strategy that was introduced for abstract equation in my thesis in 73, which is based on the following thing. You introduce an operator based on the resolvent. So what you do here, you take a curve C sufficiently smooth, and you go around to include only the unstable eigenvalues. And then you introduce this operator P, this projection, which is the resolvent, computed over this C. And you apply this projection, so the space become the direct sum of two non-orthogonal parts. One is unstable U of dimension n. The other is stable because there's analyticity of the semigroup consisting of the eigenvalues on the left-hand side. And then you take the restriction of the original operator in the unstable part, finite dimensional, and the restriction of the finite dimensional stable. Then the spectrum of the finite dimensional are all the unstable eigenvalues. Instead, for the stable, they are from the stable n+1 to infinity. And then you decompose the dynamics. So the dynamics is divided into a finite dimensional, fully unstable, and an infinite dimensional characterized by the n. And then on the finite dimensional, this is the equation that you want to stabilize. So this operator is n unstable eigenvalues. And then here the issue, you want to stabilize by a static feedback, but with an arbitrary large decay rate. And then in order to do that, you need a result essentially of Kalman. But before doing that, let me say what is the Besov spaces in question here. So you introduce Besov spaces for the reason that I mentioned before. It's essential for the boundary based, but not necessarily for the interior. So the Besov space is nothing but the real interpolation spaces between LQ and W with the two indices, in the so-called K method due to Peter. And these indexes that do the job here are m equal 2 because there's the Laplacian, and then this other index S here is 2 minus 2p. So this is the Besov space that we look at, but it's not entirely. You quote a Mann book here, and then if you take the interpolation between the Q sigma and the Stokes, the domain of the Stokes operator, in this range, when this index 2 minus 2 over p is greater than 1 over q, the q is the dimension of the order of the space, then you end up with a space which also has an additional compatibility condition, which you don't want. Instead, when this index is less than 1 over q, then the compatibility condition disappear, and you get only the condition which characterizes the space Q, as I mentioned before. So the space that does the job of which we will consider from now on is the space, the subspace, if you like, of the Besov space. So B sub tilde, where these indices are exactly over here. So since D is greater than since the Q is greater than D, so for dimension D equal 2, the index is very tight, it's between 1 and 4 over 3. But for D equal to 3, the index P is very tight, between 1 and 6 over 5. Okay, so the space in which, the Besov space in which we work is exactly this, because there's a boundary condition, which is the one of the space, and does not have a compatibility condition. And then you end up exactly with the Kalman condition in order to stabilize with an arbitrary decay rate at the finite dimensional. And the condition of the rank condition is given here. you look at the eigenfunction of the, for each eigenvalue, you look at the eigenfunction of the adjoint, and then you know, for I, 1, 2, up to Li is the geometric multiplicity. But these are, you know, this in the product, if you like, the duality pairing, are only in little omega. So you want these vectors for each eigenvalue, you want these vectors of this eigenvector to be linearly independent in little omega. Of course, they are, to begin with, they're linearly independent in big omega. And so that's what the issue is. And as a result of that, you can construct explicitly infinitely many vectors in such a way that if you can construct a control, finite dimensional control, which right now is open loop, such that not only the solution but also the control decays in the LQ uniformly, but also in the Besov uniformly. But so far is only open loop. But in fact, you can say explicitly what it is. It's under the finite dimensional spectrum, but the general case is very, very complicated. So I just wrote the simplified case when there is the eigenvalues, the geometric and the algebraic multiplicity coincide, but the result is fully general, but it's very, very complicated to write. So the feedback now, this operator that does the job can also be written in a feedback form, is given here. So you have eta sub n, the finite dimensional dynamic, and the control is given here in the feedback form. And it has the property that we want to do. So how do you satisfy this rank condition of the Kalman rank condition? And here's the story. And there is a proof here, which I will skip, but it's based, at the end of the day, is based on a unique continuation result of an eigenfunction problem. So the eigenfunction problem is this. You have I do just for the original, although should be done really for the adjoint. This is your eigenfunction problem with divergent phi. And you have an additional overdetermined condition that this is also 0 on this little omega, and you want to conclude that this is W is 0, in fact, in big omega. So they go from the small to the bigger. And in terms of the original MHD equation, the result is this. So you have a two equation coupled. So the eigenfunction lambda phi and lambda xi. Here the dynamics is phi all along, coupled with xi. Here xi coupled with phi. So this is an eigen up to here is an eigen problem, and there will be infinitely many, in fact. But then there's an additional overdetermination. So you want the solution here the determination is that the solution be identically 0 in little omega. And what you want to do, you want to conclude that the solution, in fact, is 0 over the entire omega. And this requires this unique continuation with the Kalman type of estimate and so forth. As a result of that, you get that the feedback linear semigroup is analytic and is in fact decay exponentially with an exponent you can given here, which after you do arbitrary decay rate of the finite dimensional, you can do for the infinite dimensional but still linearize. You can do for, if you like, with the decay up to the minimum decay up to the first real part of the first stable eigenvalue. Then you want to go. You can do not only for the QLQ, but also by interpolation, you can do also for Besov, which is given here. So the linearized feedback in the Besov space is, it decays exponentially with this control, which has been obtained explicitly in the way said before. And then you pass to the nonlinear part. The nonlinear part, now you go back to the translated. You call the translation Z curly B, you call it Xi. And this is a nonlinear, so this is a nonlinear problem in a feedback form with the same feedback operator, the same feedback form that you had for the linear. So they are the vector P that has been constructed for the linear, the vector Q that's been constructed with the linear, and you look at the nonlinear problem. So you look at the variational parameter formula, and you look at the right-hand side as a point, as an operator. And what you want to do, you want to show that this operator is a fixed point. And so, as I said in the past, you need the maximum regularity, original QQ, and also for T equal infinity, because the for the linearized linear problem. Linear problem is infinitely stable, and therefore T is infinity. For the Hilbert space is equivalent analyticity and maximum regularity, but for Banach space you have to do extra work, which is not trivial. So the maximum regularity I given here, for instance, for this operator, which is a dominant operator, you look at variation parameter formula, you start with f in a certain space here, and you want to look at the integral of the variation parameter, the gains absorb the operator AQ in front. So this is the maximum regularity. And then for the homogeneous problem, you look at the feedback problem given here, and is given by what? Is given by the original linear plus this term here, which is a feedback. But this feedback is a nice operator, is bounded. And so maximum regularity, under bounded perturbation is fine. And so you have that the feedback operator is uniformly stable, not only in the QLQ, but also in the interpolation, and consequently in this Besov. For the index of in the very tight indices, which, as I said, P between 1 and 4/3 dimension 2, but is even tighter with P between 1 and 6/5 in dimension 3. And then the Wolposeness of the nonlinear is the following. You start with the dimension 2 or 3, Q, as I said before. You start with a positive, so there exists a positive constant, which is identified in the proof, such that if initial condition in the Besov topology is less than R1, then the operator of the variation parameter formula is in fact, which is given here, is in fact a unique fixed point, define a unique fixed point nonlinear semigroup in the space of maximum regularity. So the chi here becomes the chi here. So this is the solution of the nonlinear problem locally. And the space is the space of maximum regularity, which is given by LP0 infinity because the infinite stabilization, uniform stabilization, and then the domain of the linear or linearized or feedback operator. And then this becomes W2, and then this space is known to be continuously embedded in the space C infinity B. And so these spaces here are the spaces of maximum regularity. Then you go back to the original problem. So not only have a unique continuity, not only have well-posedness locally, but also with the same, perhaps by making the initial sphere sufficiently small, even more, then you get the solution decays exponentially with respect to the origin, because this is a translated problem. So you go back from the translated to the original, and then you start with for the original, therefore you start with the original, the indexes here, dimension 2, dimension 3, and then you start with the ball in the Besov spaces, such that the distance between element in this ball from the equilibrium solution given at the very beginning in the fluid, and also the magnetic field is less than rho. And then the result is that here. Okay, so the result is that if you look at the problem here, which is now with this control given in feedback form, within no linearity there, you get the system a unique solution for sufficiently small data sufficiently close to the equilibrium solution in the space of maximum regularity. And in fact, the distance between the y and the b with respect to the equilibrium solution decay exponentially in the Besov norm. Okay. Now, what are about the references? I have one or two references here. One is the references here. There was a proportionality, infinite dimensional feedback given here. This has to be sufficiently large. The support of this has to be sufficiently small, so etc. This is not in the context. The other problem was this Lefter, which has the same technique, but in the Hilbert space. And it's finite, the operator is finite dimensional, but it's not identified what it is, what is the dimensionality. And of course, this is also the Besov space, which requires showing the not only the analyticity, but also the maximum regularity. I have a bunch of references, and I think I'll stop here because I think I went a little bit above. Okay, thank you.
Okay, thank you very much, Roberto, for this nice talk, very technical also. So are there any questions or comments from the audience? You can use your microphone, or also you can write your question in the chat.
Okay, I would like to ask a question. Thank you very much for your talk. I'm interested in control reduction. I mean,
Control what?
reduction.
Or reduction.
To use less components as equations. So is it possible to what can you say? What can you say?
Yeah, okay. I can say you look, okay, if you look at the Boussinesq, not for the MHD, but for the Boussinesq, yes. For the Boussinesq, let me say it's a very technical issue, which is nice that you raise it. Look at the Boussinesq, okay? So Navier-Stokes coupled with the thermal. The Rhine condition, etc., are always given in terms of the adjoint problem, not the original problem. For Boussinesq, where you go from the original problem to the adjoint problem, there's a big difference. For Navier-Stokes, if you do the original problem and the adjoint problem, who cares? They're just they're more or less the same thing. But for the Boussinesq, there is a component, a vector, which is orthogonal, a very special 1, 0, 0 in the thermal component. And when you go from the original problem to the adjoint, okay, the adjoint is better, is nicer. And therefore, we go back to what you were asking. Since the adjoint problem for which you have to find this Rhine condition is nicer, there are also unique continuation problem for the adjoint for the Boussinesq. But since it's nicer, then you can take the control to be nicer than smaller than the dimension of the space, which is exactly what was your question. So for Boussinesq, yes. Navier-Stokes, no. And the MHD, no. Here, the emphasis in this MHD is to find the minimal number of control, finite dimensional, not only finite dimensional, but also minimal, and also explicitly, the proof is explicit. Somebody wants to do the numerical analysis, I would love to see this. It can be done explicitly, and the control are minimal. But the question you were asking about the dimensionality with respect to the space, that's okay for the Boussinesq. We have the problem that the papers I mentioned before, for instance, even for the interior, they do treat this problem. And was done also for the controllability by some other people, I think Oron and other people in the controllability, but this is stabilization. So the question that you ask is valid and applies to Boussinesq, but not to MHD or to Navier-Stokes.
Okay, thank you.
Okay, other questions? Juan?
Okay, can I ask a second question?
Yeah, of
Yes,
course.
sure.
Oh, another variant of the problem you have introduced is the boundary control case. I mean, can you extend these results to the use of a boundary control?
Okay, yeah. Okay, let me start with the Navier-Stokes, okay? Because if you don't do the Navier-Stokes, there's no way to start doing also the Boussinesq or the MHD. For the Navier-Stokes, the situation is the following. For dimension d equal to 2, we had a paper with Irene in 2015 where the feedback control were finitely many. The technique was the usual technique using optimal control, Riccati equation, blah, 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 etc. But When it goes to, for that technique, if you go to d equal to 3, there was a component that was infinidimensional. And that infinidimensional component of the feedback becomes 0 if the initial condition are compactly supported, which is the reason why for 3 dimensions equal to 3 was absolutely essential to move away from Sobolev setting to the Besov setting. Not only, but the technique is no longer, is no longer, of course, a Riccati equation, is a spectral equation. So in the case of however, the situation is even more complicated than that. We want to do for boundary, we want to do an arbitrary small portion of the boundary. And the question related to the answer related to the question is the following: can I do for the Navier-Stokes, can I do feedback stabilization with the feedback on an arbitrary small portion of the boundary period? The answer is no, it's impossible. There is a counterexample of this unique continuation property of the two French, the name is Lebeau, and just a very simple counterexample in 2 dimensions, even with the Stokes, let alone the Oseen operator. They show that you cannot do it. So you cannot do stabilization of the Navier-Stokes dimension equal to 3 with the control on an arbitrary small portion of the boundary. You have to put a little bit extra interior, arbitrary small, and then you put a control in the interior tangential to the boundary, so tangential. And without this little control also in the interior tangential to the boundary, you cannot do purely control on the arbitrary portion of the boundary is impossible. And this is exactly related to the fact that this counterexample of Lebeau, etc., in 1995, I think, is an older counterexample, and is a nice, very simple in high half space, which can then by partition of unity can become an arbitrary small portion of a bounded domain. So you cannot do stabilization on a small portion of the boundary, only the small portion of the boundary. You have to do also a little bit of interior control. So this is a dimension equal 3. Okay, so that's the situation.
Okay, thank you very much. Thank you very much.
Thank you very much. Other questions? So if not, so we are a little bit tired. So we thank you very much, Professor, for this wonderful talk.